Welcome back to The Deep Dive, the place where we unpack the latest in machine learning research.
Great to be here.
So today we're diving into a paper called OSMa-Bench, evaluating open semantic mapping under varying lighting conditions. Now, if you're keeping track of robotic perception, spatial understanding, this field moves fast.
It really does. And this paper hits on something pretty fundamental.
Yeah, it seems like it. It's looking at how well robots can actually, see and make sense of their environment when the lighting isn't perfect, which is most of the time, right?
Exactly. This research zooms in on open semantic mapping, or OSM.
Right.
Basically giving robots the power to build these really rich, understandable maps, identifying objects, understanding relationships, all using natural language.
Without needing to be pre-trained on every single possible object it might encounter.
Precisely. Open vocabulary is key. But the real kicker this paper addresses is lighting. Real-world lighting is messy, it changes, and that can seriously mess with current systems.
Okay, so for listeners really into robotics, this is hitting a practical pain point. We see these cool demos, robots moving around, pointing things out.
Yeah, often in quite controlled settings.
But this work is saying, hang on, just the light changing in a room could trip them up.
That's the core concern they're investigating. And to do that properly, they've built new benchmark.
OSMa-Bench.
OSMa-Bench, that's it.
Yeah.
It's a dynamically configurable benchmark, specifically built to test how robust these OSM systems are under different lighting.
Dynamically configurable. What does that mean in practice?
It means they can set up various scenarios easily. They actually created new data sets by taking existing ones, like ReplicaCAD and HM3D.
Okay, I know those. Synthetic and real-world scan data.
Right. And they extended them to simulate a whole range of lighting baseline, just a camera light, even dynamic lighting that changes as the simulated robot moves.
Oh, interesting. So they're really stressing the systems.
They are. And they've also added things like varying the robot's speed. Plus, crucially, they've automated the evaluation using LLMs and LVLMs.
Large language models and vision language models, like Gemini you mentioned.
Yeah, they use Google Gemini. The idea is the AI generates specific context-aware questions about the scene graph the robot builds.
So instead of a person manually checking the map, the AI asks things like, what? Is there a plant next to the window?
Exactly. Or how many chairs are at the table? And then it automatically checks the robot's answer against the ground truth data from the simulation.
Okay, that sounds way more scalable and objective than manual checks. Standardized testing, really.
Yes. It allows for much fairer comparisons between different OSM methods. So they're looking at several things.
Like what?
Well, 3D semantic segmentation accuracy. How well does it label the pixels or points belonging to each object?
AMIOU and accuracy metrics, I assume?
Yep, MAC FFMIOU. Also, basic object existence. Does it know if a specific object is even there? Detection completeness. Did it find all the chairs, for instance?
And the spatial reasoning part, the relationship.
Critically, yes. Can it answer those questions about where things are relative to each other? That's a huge part of real understanding.
So before OSMa-Bench, what was the landscape like? There's been work in this area, right?
Oh, definitely. You had advances in open vocabulary 3D scene, understanding things like concept fusion, concept graphs, open fusion, trying to get robots to understand scenes without predefined lists.
Right, moving beyond just chair, table.
Exactly. Then there was language-guided segmentation, like OpenScene and OpenMass3D, letting you point to specific things with language.
Segment the red chair.
Something like that. And also work focused specifically on robustness, benchmarks like BBQ, PLA, Space 3D Bench, trying to make semantic maps more reliable.
But the gap was lighting.
Pretty much. A lot of that prior work, while valuable, often evaluated things under, let's say, ideal or at least consistent lighting. There wasn't a standard way to really hammer on the lighting variation aspect.
Which is everywhere in the real world.
Absolutely. So OSMa-Bench fills that gap. It's specifically for testing robustness to light changes.
Okay, so they built the benchmark, then they tested some existing methods. You mentioned concept graphs, BBQ, OpenScene.
That's right. They ran these 3 state-of-the-art approaches through the OSMa-Bench gauntlet using the ReplicaCAD and HM3D datasets with all the lighting variations.
And what did they find? What's the bottom line for folks wanting the quick summary?
Well, it's nuanced, as you'd expect. Concept graphs generally got the best overall accuracy for identifying what objects were, the max score.
But there's always a but.
But it struggled a bit more with smaller objects. Some has mythed them or misclassified them.
Okay. What about BBQ?
BBQ was faster, computationally lighter, but, and this is key, it was the most sensitive to the lighting changes. Its performance dropped off quite significantly under dynamic or poor lighting.
So maybe not ideal if the environment's lighting is unpredictable.
Probably not, based on these results. OpenScene, on the other hand, showed more stability. It had the best overall FMIOU, which suggests the quality of its segmentation masks held up better across conditions.
Why is that, do they think?
They suggest it might be because OpenScene relies on richer semantic descriptions from its underlying models. But the trade-off was that the precision of its segmentation outlines wasn't always top tier compared to others.
So different strengths and weaknesses, and lighting really brings those differences out?
Exactly. You can see it in their graphs and tables. Performance metrics change, sometimes dramatically, depending on the lighting setup and the method.
You mentioned weird cases, too, like shadows causing problems.
Yeah, they highlighted some specific failure modes or corner cases under tricky lighting. Shadows sometimes got segmented as objects or attached to nearby objects incorrectly.
I can see how that would happen.
And uniform surfaces, like a plain wall, became harder to segment accurately when the light was moving dynamically across them.
Makes sense. Creates false edges or washes out real ones.
Right. And with only the robot's camera light active, the point clouds could get noisy, making everything harder.
What about the language side? Any issues there?
Yes, some interesting points. Sensitivity to slightly different descriptions, like distinguishing wall cabinet versus base cabinet, could be brittle. Even things like extra spaces and class names sometimes messed up segmentation for some methods.
Wow, that's specific.
Apparently so. And object merging or splitting was another issue. They gave an example where a staircase got segmented into individual steps.
Which would totally mess up answering a question like, how tall is the staircase? Right.
Precisely. They showed an example question about measuring stairs where that exact problem led to a wrong answer. So the mapping errors directly impact the downstream reasoning.
So the VQA, the visual question answering part, how did that hold up?
Well, they tested BBQ and concept graphs on this. Accuracy was pretty high for simple, does object X exist type questions, binary existence.
Okay, so they generally know if something's there.
Yeah, mostly. But accuracy dropped more noticeably for questions about object attributes, color, material, and especially spatial relationships when the lighting got challenging.
Which, again, links back to the real world. If a robot can't reliably tell what's next to what under dim light, that's a problem for a navigation interaction.
It's a huge problem. You need that robustness. You can't just assume perfect lighting in a factory or a home or a hospital.
And this domain gap issue you mentioned, models trained on web data versus robot sensor data.
That's a big factor they highlight. Web images often have very different characteristics, lighting, viewpoints, clutter, compared to what a robot perceives navigating a 3D space.
So models trained primarily on that web data might just not generalize well to the robot's actual input, especially under difficult conditions.
Exactly. This paper really underscores that gap and the need for systems trained or adapted to be resilient to these real-world variations. OSMa-Bench is a tool to help drive that.
It definitely shines a light, couldn't resist, on these persistent challenges.
Indeed.
Okay, so this work sets up the problem and provides a tool. Where do we go next? That leads us nicely into our novel notion segment. What future research could stem from this?
Right, so one idea, given how much lighting impacts the visual features, maybe something like adaptive illumination-aware feature fusion.
Okay, unpack that a bit.
The idea is, if the system can sense or estimate the current lighting conditions, maybe it can learn to dynamically weight the visual features it extracts.
So trust features extracted under good light more than features from shadowy areas.
Sort of, yeah.
Yeah.
Or maybe learn to combine features extracted under different simulated lighting conditions during training to build a more robust overall representation.
Like creating features that are inherently less bothered by light changes.
Exactly. You could potentially use techniques like meta learning, where the model learns how to adapt its feature extraction based on the lighting it detects. It's kind of related to domain adaptation concepts in ML.
Interesting. Training the model to be smarter about trusting its own eyes, depending on the light. What's another angle?
Another one, building on those corner cases and errors they found, is about incorporating uncertainty more explicitly.
So not just saying that's a chair, but that's probably a chair, I'm 80% sure.
Precisely. Representing confidence scores for detections, segmentations, even the relationships in the scene graph. So the map isn't just definite statements, but includes how sure the system is.
And downstream tasks could use that uncertainty.
Yes. A navigation planner might avoid paths near low confidence objects or A manipulation system might grasp an object more carefully if its segmentation is uncertain.
That sounds like probabilistic robotics, right? Applying that to the semantic level.
Exactly. Using belief states not just for location, but for the semantic interpretation of the environment. It could make robots much safer and more reliable when dealing with the ambiguities caused by, well, things like bad lighting.
Makes a lot of sense. Moving beyond just mapping to mapping with confidence levels. So OSMa-Bench seems like a really valuable contribution here.
I think so. It provides a standardized way to measure something critical that was perhaps overlooked in systematic evaluations before.
It really pushes the field towards building robots that can function reliably outside the lab in the messy, unpredictable real world. For our listeners who want the nitty-gritty details, the paper link is in the show notes.
Definitely worth a read if you're in this space.
And it leaves us with a big question, doesn't it? As robots get better at genuinely understanding their surroundings, even under tough conditions, how does that fundamentally change what they can do for us?
That's the billion-dollar question, really. It opens up so many possibilities. Definitely some food for thought,